So for those of you who are registered, this is the code of the course. It's an introduction to quantum field theory in course spacetime. And this is a pass-fail course. I will explain the details later on. And we will have the class here, even though we are back here, but we need the camera. Okay, can you go yourself? Okay. Do I have you in my... So, before going through the program, let me say a few words about the whole course, and in particular about this field. So, I'm sure that you know that quantum field theory is one of the cornerstones of modern physics. The standard model of particle physics was built upon it, and its formulation and experimental verification was one of the most successful chapters in modern physics. So quantum field theory is a very nice tool nowadays. The only point is that it doesn't include gravity. It includes the weak interaction, the strong interaction, and the electromagnetic interaction, but doesn't include gravity. And we have learned that every time we have a new interaction interacting with the other ones, we find new phenomena. So what about gravity? Can we include gravity with the other fields and see if we find new phenomena? The bad thing with gravity is that it's very difficult to quantize. We have been trying to quantize gravity for more than 50 years, and we don't have still a complete successful theory. There are many attempts, but no one can claim for success. So that is a problem. We don't know how to do quantum gravity. However, there are what happens with gravity is that it's so weak that its quantum effects are only manifest at very extreme regimes, what we call the Planck scale, when energy, curvature, temperature gets to the Planck scale. And the Planck scale in energy is something like 10 to the 19 GeV. Compare that with the 10 to the 3 TeV that we have, so GeV that we have in LHC. So it's like 16 orders of magnitude away from our experimental verification. So only in very peculiar places, like in the center of a black hole or close to the Big Bang singularity, real effects of quantum gravity are going to be important. So therefore, we have a huge regime in which gravity behaves as a classical field. So we can ask if we can learn how quantum fields and classical gravity interact, and if new phenomena appear when H bar is only on the matter part, it's not on the gravity part. Can we do that? This is precisely what quantum field theory in core spacetime is going to be. So if you want, so quantum field theory in core spacetimes is going to study the behavior of quantum matter fields. So we have quantum field theory propagated in presence of a classical gravitational field. So again, H bar is only on the quantum part, not on the gravity part. So here, gravity is described by GR, general relativity. So what we have is a manifold. Normally I will take 4-dimensional manifold and a metric G mu nu defined on it. So it's a Lorentzian metric with signature minus plus plus plus. And for matter, we will have a standard quantum field theory. So you can see that that the amount of speculation in this framework is not huge, because we are going to have gravity and quantum field theory in a regime in which we are confident about both, in a regime in which curvature is far from the Planck scale, and so GR is studied, and in a regime in which quantum field theory has been well tested. So we have some trust on these two mathematical ingredients. So in addition to that, if the effects of matter in gravity can be neglected, which will happen in many circumstances. So you know that matter has energy, has momentum. It gravitates. It will modify the gravitational field. But there are some circumstances in which the matter field that we study modify the gravity in a negligible amount. So we can neglect those effects. So if that happens, we will say that there is no back reaction. Then we will work with a fixed metric, and dynamics of the metric will be unimportant. Many of the effects that we will study will have that approximation. We will assume that matter doesn't modify the gravitational field, so we have a fixed metric, and we don't care about the dynamics of gravity itself. So an example, the first derivation of black hole evaporation by Hawking uses this approximation. If not, in circumstances in which the back reaction of matter into gravity is important, then the dynamics of gravity is important, and the dynamics of gravity will be given by what we call the semi-classical Einstein equation. So we will assume that the source of the gravitational field, of a classical gravitational field, is the expectation value of the quantum energy momentum tensor. And this is called semi-classical because this source is quantum, but gravity is classical. This is just an introduction. I just want to give you a flavor of what we are going to do. And I want to say this because with this I can tell you what is the regime of validity of this framework. The regime of validity will be always when energies, curvature, temperature, etc. are well below the Planck scale. So if we are in that regime, our approximations should be valid. But more than that, because we want to write these kind of equations in which gravity is classical but matter is quantum, the quantum fluctuations of the energy momentum tensor of matter have to be much smaller than 1. So, because if the quantum fluctuations of this guy are huge, then the quantum fluctuations of the metric cannot be neglected. One has to do quantum gravity. But in regimes in which these quantum fluctuations are small, we should trust this equation, and this is what people call semi-classical gravity. And we will discuss how to do that. In particular, how to give meaning to this kind of objects, which is not real. So this is our goal. So this is an introductory course. I know that many of you never took a whole course on quantum field theory, for instance. So it will be introductory. And also, for reasons of time, I will focus on free fields. So I will do free field theory, or in other words, non-interacting field theory. And there are several reasons. One is because, as I said, introductory course and reasons of time. Second, because interactive field theory in coarse spacetime is not well developed yet. Some people do computations in highly symmetric spacetimes, like the Sitter or other type of highly symmetric spacetimes. But there is no rigorous formulation of an interacting quantum field theory in an arbitrary spacetime. So this is something that people is working on right now. And the third reason is that many interesting phenomena, many new phenomena appear already for free fields. So we will find really exciting new phenomena appearing in that situation. So we will describe many examples. For instance, maybe the first example was when Leonard Parker discovered that the expansion of the universe can create particles from the vacuum. So you have a free field propagating in an expanding universe, and particles may appear spontaneously from the vacuum. That will happen for free fields. The Hawking derivation that black holes can radiate thermal particles of a quantum field also happens for free fields. The derivation of how the primordial universe was able to create density perturbations that later on grow and form galaxies and galaxy clusters. That is also done in free field theory in quantum mechanics. So many of the hot topics that people are discussing nowadays in gravity are based on free fields in core spacetime. So this is an interesting enough subject to complete one semester course on this topic. So what else I want to say? I want to say also that it is my experience that learning quantum field theory in core spacetimes, one learns a lot about quantum field theory in flat spacetimes. And the reason is that when you want to generalize a theory, in any theory you have ingredients which are primary and others which are secondary. Ones which are the key element of the theory, and ones which can be derived from the key elements. And when you want to generalize that theory from flat to spacetimes, you really need to understand which are the key elements, and those that can be generalized, and throw away those elements which are not essential, which are just specific of flat spacetimes. That happens quite seriously in this framework. And the reason is that the standard way of learning quantum field theory or formulating quantum field theory in encoded spacetime relies a lot on Poincare symmetry. Poincare symmetry is just Lorentz transformations plus translations, space and time translations. And even if you don't realize, the standard formulation of quantum field theory in encoded spacetime relies a lot on Poincare symmetry. I can tell you, and we will see that in detail, that the definition of vacuum has to do with Poincare symmetry, relies on Poincare symmetry. The definition of particle, what do you mean by particle, relies on Poincare symmetry. And normally, we are so used to the notion of particles that we call quantum field theory sometimes particle physics. But that is just an artifact, not an artifact, but it depends on hands-on from Poincare symmetry. But when we generalize on arbitrary spacetime, we don't have Poincare symmetry anymore. So all those notions have to be revisited. You have to formulate the theory in a different way. So you really have to come back, think about what are the key elements, what are the essential elements of your theory, and what is secondary, and then generalize it. And then you learn that what you really have is a field theory, it's not a theory of particles, and you can make a self-consistent theory of fields propagating in an arbitrary spacetime, where the notion of particle is secondary. You can define particles in certain approximations, and they are very useful, but they are not at all generic, not even objective. You can define one notion of particle, and I can define a different notion, and we may disagree with the particle from some quantum state. So that is the point, that we will learn a lot, I hope, about quantum field theory by generalizing to core spacetimes. And regarding conventions, I will use for the signature of the metric minus plus plus plus. I will use units in which the speed of light is equal to n, but I will keep h bar and g explicitly just to emphasize where quantum mechanics appear and when gravity appears. That is a nightmare for me because, you have to look where h bar goes, and most of the books, they don't have h bar, so I am spending a huge amount of time. I am regretting of my choice, but now it's too late, so I have to keep going with that. And so that will mean that, if c is equal to 1, normally we have units of length, energy, and mass. If c is equal to 1, length and time are the same, because this is speed, and also energy and mass are the same. But because h is different from 1, energy and time are unrelated, so I will have 2 units, length and energy. And when I work out dimensional analysis, I will tell you what are the units instead of length and energy. Action, for instance, is length times energy, etc. So, and if I don't consider electric charges or other kind of objects, with this I have more than it. What else? Fourier transforms. So regarding Fourier transforms, my conventions is that, a function of x, I will put the 2 pi in this in going from k to x, in going from a to k, then I don't have. I will not have 2 pi. And every time I have Greek indices, they run from 1 to 3 if we are in 4 dimensions. If we are in n dimensions, they will keep going. But they include time, so they are space-time indices. And I and j, k, etc., like in indices, they just are spatial indices. And when I write x in this way, I mean space-time. And when I write x with an arrow on the top, I mean just spatial time. And this is all the conventions that I wanted to emphasize. Now I can explain you the table of contents. So first of all, regarding the time, we are planning to meet here for 36. If everybody agrees, we can move the class a bit earlier on Tuesdays. On Thursdays, we have the colloquium 3:30, 4:30. So it's a bit tight, and we cannot move it earlier. But on Tuesdays, you may think about it, and next day you can tell me who wants to move it a bit earlier. I'll be happy to have the class earlier. If you have another class, then we can. Please think about it, and you can tell me. So regarding the program, so I have taken into account that there is a broad audience here. As I said, there are students who never took a course on quantum field theory. So my goal is to reach everybody. So what I have done is add a couple of lectures at the beginning, so to put everybody at the same level. And I don't think that is bad. I think it's even good for me, because starting from scratch, you can emphasize what is really important. Just revisiting a little bit how you quantize an harmonic oscillator, how you quantize a time-dependent harmonic oscillator, how you quantize a free field in viscosity. I can re-emphasize what are the key objects that are going to be generalized later on. So it's good for me, and it will save me a lot of time later on. And I think it's even more pedagogical, because many of the features of field theory in quarter space-time already appear for a single harmonic oscillator with frequency time dependent. So I think it's much clearer for you if many of the concepts are introduced for a single harmonic oscillator without the complications of field theory. And then when we go to field theory, it will be much easier. So with that in mind, I will start describing very briefly the standard time-independent harmonic oscillator in one lecture, lecture 1. In the second lecture, I will do quantum field theory in flat space-time. Maybe that will take me more than one lecture, but I think it's a good exercise to review that content. It will be easy, because if you understand how to do an harmonic oscillator, a quantum field is quite straightforward. Just putting infinitely many harmonic oscillators together, where the complications are in the infinitely many. This is where everything gets complicated. Then third lecture, as I said, I want to do in some detail the time-dependent quantum harmonic oscillator. Because all these effects of, multiple possibilities for the vacuum state, multiple definition of quanta, particle creation, that already appears for a single time-dependent harmonic oscillator. And then with that material, I will go in the fourth lecture, the fourth one, into quantum field theory in core, the same time. But that will be quite easy because most of the hard work will be done before that. And then with that, we will have the theory on the table. All what we have to do is to work out applications. The first application is quite shocking. Is the application in which you realize that the notion of particle is just a convention. It's not something objective that everybody will agree on what a particle is. And that is what we call the unproven thing. That happens already in cosmic space-time, but when you involve non-inertial observers. So we will compare the quantification of an inertial observer and the definition of particle for an inertial observer, and that for an accelerated observer, uniformly accelerated observer. And they will disagree on many things. It's called the unproven thing, and it's quite illuminating because it already happens in flat space-time. In chapter 6, I will describe the first, historically, the first derivation in quantum field theory in cosmic space-time. This is the creation of particles in a free-Marulenet traversal Walker. In 7, I will describe the Hawking derivation of black hole and the physical implications. Like black hole evaporation is quite hot topic in gravity nowadays. Today we were discussing about the new paper by Hawking, Strominger, and Perry about black hole evaporation. So people is, even Hawking is still discussing topic. So there is a lot of stuff to learn on that topic. And then in 8, I will describe what for me is one of the most beautiful applications, beautiful and important, which is the creation of primordial perturbations in the early universe. Lecture 9 will be about renormalization in core spacetimes. Renormalization has to do with dealing with the problems arising from the infinitely many degrees of freedom that we have in a quantum field. So a quantum field has infinitely many degrees of freedom because you need to specify the field at each point of space, and there are infinity points. And because of that, infinities appear in the formulation. And how to get rid of those infinities and extract physical predictions from the theory is called regularization and renormalization. And we will describe that in lecture 9. So, and in the last chapter, I will go to a more formal construction of the theory, and I will describe in a second why I want to do that. So, there is part of the program missing. I will give you later. You have it? You have it. So, okay. Most of you don't have that. So, regarding textbooks, there are not too many, but there are a few of good textbooks in the library. So I have written them here in order of date where they appear. So the first one is by Parker and Tons, 5 or 6 years old. One by Wall, Peter and Davis. They are excellent books. They are very good books. But in my opinion, the literature is quite polarized. So I find books which are quite pedagogical in the sense that they are formulated in a way that you can easily follow that. But I feel sometimes that they miss conceptual and mathematical content. That reading them, you really don't appreciate many important points in quantum field theory in corpus design, like the existence of inequivalent representations and other important things. On the other hand, there are books which are on the other extreme. They are extremely difficult with them to do computations and to do explicit derivations, but they are extremely clear in the mathematical and conceptual content. But there is nothing in the middle. It's very difficult to connect them. So, because of that, that in fact was my motivation to teach this course, to do something that extrapolates between one formulation and the other. So, with that in mind, I will not follow any book in particular. So, what I'm going to say, you can find it in one way or the other in some place. Most of it, some part is just by my own. But I will not follow any book because I want precisely to do that. I want to start with a language which is familiar to most of you, which is easy to understand and easy to do computations with, And little by little, make the theory more rigorous and more mathematically formulated. And so in particular, the last chapter is about that. The last chapter is about taking all what we have learned and, and just once we know how to apply it and how to extract physical information, just reformulate it in a way which is crystal clear what are the mathematical structures, what are the key mathematical objects in the formulation, how, and what mathematical consequences we will have of that theory. So, and I hope that at the end we will close the course and we will have a quite good picture, quite good understanding, good and big understanding of what is the physics of quantum fields in the same times. If we have time, I can include also fermions, like spin 1/2 fields, spin 1/2 fields, and or the quantification of the electromagnetic field. But I am afraid the course is too short, so I don't know. If we have time, I will include it. If not, I will not. But I believe that if you understand these 10 chapters in a deep way, you will learn a lot about quantum field theory, and you will be able to learn by yourself other points that I don't have time to cover in this chapter. Regarding exam and homeworks, there will be no exam in the course, so the grade will be obtained from homeworks. I will not give you some homeworks every week. What I'm going to do is, every time there is some derivation, which I believe is more or less straightforward, I will ask you to do it. I will write in red check, and you will do it, and next day you will give me. This is a pass-fail course, so there is no pass or fail. So I will not be super strict. So if you don't know how to do something, just don't do it and ask me, and we can do it together or add. So this is supposed to be an advanced course, so I will be more relaxed than introductory course. Any comment or any question?
You said we only have 1 or 2 days for each homework. Well, I suppose.
I mean,
do it on Thursday.
You can do it 7 days after. Or if you give me the 10 days after, that's fine. Detailed then. Of course, if at the end of the course I realize you didn't give me anything, you will tell. But if you work normally, I will. And I know you. Any other comment or question? Who? All of you had a course on quantum field theory before? I know. You didn't? You had. You had. The rest. So it is worth to start from scratch. Okay, so if there are no questions, we can start with the material of the law. Rajesh and Esteban, if you have questions, you can also ask. David and Lydia. So the first chapter is something that all of you know very well. So it's the quantum harmonic oscillator at weak frequency. It will have 2 sections. One is the classical theory. The second will be quantum theory. The Fock representation. So let's start with the classical theorem. So here our system is quite simple. It's just we have some particle of mass m attached to a spring with coupling constant, spring constant k, time independent. So we'll use the letter x for deviations from equilibrium position. So k is time dependent. You know very well how to write the Lagrangian of this system. The Lagrangian is just kinetic energy plus potential energy. Important is a time dependent harmonic oscillator. So k is time independent. So from the Lagrangian, you know how to compute the conjugate momentum. P is just given by the derivative of the Lagrangian with respect to the velocity, and it just, if you do the derivative, is just mass times the velocity. You also know what the Hamiltonian is, representing physical energy and generating time evolution. So the Lagrangian arises from a return transform, the Hamiltonian, and it just the total energy.
Am I confused, or should there be a minus sign in the second one?
Thank you. So we can compute from these quantities the equations of motion from either Lagrangian or Hamiltonian via Euler-Lagrange equations or Hamilton's equation, and you know that they are just second derivative of t, omega squared x of t equals 0. I will call this equation 1. Where I have just defined omega to be the positive root square of k over n. I will try to work out, to write the dimensions of the different quantities that we have. So the dimensions of omega is time right, 1 over time, or 1 over length, because I just write 1 over time. So why I'm writing these elementary things? Because I want to tell you something about the solutions of this equation. So equation 1.
Right now there is no C in what it is, right?
There is no C. This is non-relativistic.
Yeah. So like, why are you taking L equal to B? Like even with C is not involved.
Because these are the units I am using. I am using units with the speed of light equal 1. So
So C is still equal.
C, even though there is no, even if I put C different from 1, it will not appear in this equation. I am still taking C equal 1, so space and time have the same units in my equation. All the cars I will take those units. So what I want to say is that equation 1 is a second order ordinary differential equation, and therefore, first of all, two properties. A solution is solution of that equation, x of t, is uniquely determined, for instance, by specifying position and momentum or velocity at some dynamo. So if you give me initial conditions for position and velocity, there is a unique solution with that because it's a second order differential equation. So I need two initial data. So I want to say this because there is a one-to-one relation between initial positions and velocities and solutions. So if you want, there is a one-to-one relation between solutions and elements of the phase space. Elements of phase space. Recall that the phase space is just the space of initial positions and momentum. So, second point that I want to emphasize, which will be very important for the rest of the course, is the following. Since equation 1 is a linear equation, there are no powers anywhere, is linear. Linear combinations, of course with constant coefficients, of solutions are also solutions. If you have a solution, you have another one, you sum them, the sum is also a solution. Or any linear combination is a solution. Why? Because the equation is linear. These two properties allow us to say that the set of all solutions to equation 1, so the space of all solutions is a two-dimensional of all, let me say, real solutions. Real solutions because we are talking about a real harmonic oscillator. Is a two-dimensional real vector space. And that will be very important for the rest of the class. Every time you have a linear equation, the space of solutions is a vector space. And I want to call that the space of solutions with this fancy S. A convenient basis can be written as follows. So if you take, for instance, sine of omega t divided by 2 omega m cos of omega t divided by 2 omega m. This root square of 2 omega m is just for convenience later on to provide the nice dimensions. I can tell you that 1 over root square of omega m has dimensions of length over energy, square root. So this is a explicit basis of the space of solutions to that equation. Any solution will be a linear combination of these two elements. And if you don't believe me that they are two elements of the basis, we know the space is two-dimensional, so that they have to be independent of each other. So you can test linear independence using via the Wronskian of the equation. If you know the Wronskian method, you can check that these two solutions are linear. So this will be an important element in our course. That in the quantum theory, it will be very useful to define what we call the complex space of solutions, or the space of complex solutions. Very useful to consider what I want to call S with a C upstairs. The space of complex solutions. You know, in the quantum theory we use complex functions all the time, so it will be useful to define that. How do you construct this complex space of solutions? Just take these guys and do all possible complex linear combinations. So linear combinations with complex coefficients. This is precisely this something. So all possible linear combinations of these two elements with complex coefficients is what we define as the space of complex solutions. A useful basis of that space, you can already imagine what the basis is going to be. Going to be exponentials of I omega t and exponential of plus I omega t. And for convenience, I add this factor. This is a basis of the space of complex solutions. We will use this a lot, so let me give a name to this guy. This guy is just phi of t, bar phi of t, and this guy is just its complex conjugated, phi of t star. Just to give them a name. And of course, the space of real solution is just the real subspace, the space of complex solution. Therefore, the most general real solution to equation 1, so to our equation of motion, can be written as x of t. So it's going to be a linear combination of our basis vectors. A real linear combination of our basis vectors. So this is the homogeneous solution to the physics of the harmonic vector. Of course, if you want to know the conjugate momenta, you can. Only thing you have to do is to multiply by the mass and take the time derivative. So we have no, because I took A and A where A and A star, where A is of course time independent complex coefficient. Complex. So if you take any complex number here, this is something and this is the complex conjugated, so x is real. So you know, if you want, this is for arbitrary a's, this is the real subspace of the complex space of complex solutions. So this is real and that is real. Okay? This is something and this is the complex conjugated of that, so that is always real. And the same for the momentum. This is something plus its complex conjugated, so that is real. That is equivalent to writing the cos and the sine. That is equivalent. I am a bit fast because this is standard material. Where A is a time-dependent complex coefficient with dimensions. So if you work out the dimensions, A needs to have dimensions of root square of action. So dimensions of root the square of E times L. Okay, so this is the classical theory of an harmonic oscillator, and now that you have explicit solutions, you can compute whatever you want. If you give initial data, it will give you the specific solution associated with your initial data. You can compute energy, energy momentum, whatever. Not energy momentum because you are in one dimension, but whatever you need to do. So what we need to do is to go to the quantum theory. Unless you have any other question. Right. So in the quantum theory, as you very well know, X and P have to be promoted to operators, X and P, satisfying, I will use hat for the operators all the time, satisfying canonical commutation relations. So this guy at a given time, same by for all of them, have a commutation relation given by them. So how do we quantize this theory? Maybe I should put a box here because these are the main solutions. So how do we quantize that theory? Written in this way, the quantization is quite straightforward. So we can easily obtain a quantum theory in the Heisenberg picture starting from those equations. I should give them a name. Let me call them equations 2. So, we have the most general solutions. You can just make them, throw hats on them, and make them an operator. Of course, these guys are solutions of the wave equation, so they are just functions. If X is an operator, then A and A star should become operators for consistency. So one way of quickly building the quantum theory is now the star becomes an Hermitian conjugated because it's an operator. So we have here a candidate for quantum operator for the position, and here we have a candidate for quantum operator for the momentum. Sorry if I forget hats, I will forget them at some point in the future. So we have these two quantum operators. Let me put also a box here and a number to this equation. Because now I have to tell you what to do with this. These are operators where. So equation 3. So first of all, you can ask me what A and A daga operators are. So, if you want, you can take this equation 3 as definition of A and A daga. I define A and A daga in this particular way, where X is the position operator and P is the momentum operator. So this can be thought as definition of A operator and A dagger. These are A and A dagger are time independent. See, I didn't write time. They are time independent operators. They were time independent coefficients in the logical theorem. And the statement is that, you want to know what A and A dagger is that from this definition, from equation 3, one can obtain, and this is the first homework that I leave for you, the following. A is going to be equal to omega m over 2. I think the 2 should go upstairs. Maybe I am. Take the factor 2 out that. X at some initial time, T0, for instance, t equals 0. We can evaluate t at 0. Plus 1 over 2 omega m p operator. And A dagger is just the adjoint of this operator. So there is an I here. So all you have to do is to take the adjoint of this line to obtain A dagger.
In equation 3, is there a missing factor in the equation?
There is a missing factor here. Thank you. Parenthesis 1 I omega. Thank you. So what you have to do to move from 3 to that equation is just, you have 2 equations for 2 unknowns, you can isolate them, and the statement is that these guys, A and A dagger, are time independent, so you can evaluate these functions at the time that you want, because the result will not depend on time. I choose t equals 0 because then I kill the exponentials and everything is simpler. So now we have these expressions for A and A dagger in terms of the position and momentum operator at some time. And now, using the canonical commutation relations, it is easy to check, and this is the second homework, check this simple computation, that A and A dagger satisfy the following commutation relations. Of course, A with A dagger with A dagger is 0 because the commutator is antisymmetric, so there is nothing to compute here. But the non-trivial one is A with A dagger. If you do it, you will obtain an H bar, which is in agreement, consistent with the dimensions of A, where root square functions. So these are what we call the algebra of the A and A dagger operators, and these commutation relations make. This is the reason why we call A and A dagger creation and annihilation operators.
How can A and A dagger equal H bar when there's no H bar in either that or that equation?
Because that's a good question. Because you have X and P, you have to take the commutator. So commutators of X and P will appear, and the commutator of X and P is an H bar.
Ah, okay.
So if you plug this expression here and this expression here,
Okay,
you will have commutators between X and P, and this is where the H bar is coming from.
got it.
So this is a consequence of the canonical commutation relations for X and B. More questions? So just from the definition of A and A daga, these equations and canonical commutation relations, we know that A and A daga satisfy these ones, and this produces the name of creation and annihilation operators for A and A daga.
Is the computation of A for XP is independent of time?
Yes.
So for any t.
Yes, because A and A daga, they are time independent, so the commutator is time independent. For the harmonic oscillators, they are also called the raising and lowering operator, or ladder operator. In quantum field theory, they are called creation and annihilation, but they are the names. And this operator, n, defined as h bar minus 1 A daga A, is called the number operator. The reason for these names is simple, and I bet you have done this in the past. The reason is the following. I am doing this with some detail because this is what we have to do also in pure theory. So I do it here, which is simpler, and pure theory does exactly the same. Because the following. So let me call that equation 4. And the statement is that using these commutation relations, using 4, you can show that the eigenvalues of n, so n acting on some states, small n are going to be small n times n, so are non-negative integer numbers. So small n belongs to the positive integer numbers, including 0. This comes just from these computation relations. No more information. With these two lines, you should be able to prove that that is true. Second, one is also able to prove that if you act with A dagger or A in an eigenstate of the number operator, you know the result. This guy gives you something proportional to the eigenstate n plus 1, and this one something proportional to the eigenstate n minus 1, with a coefficient which is just this. And for this reason, this guy is called annihilation operator, because it annihilates one quanta of the number operator, and this guy creation. This is where the names are coming from.
So I just wanted to point out, in the usual quantum mechanical derivation of this, the H bar is absorbed into the A. You're doing something. You know, if you just pick up a graduate or undergraduate text in a harmonic oscillator, A dagger is 1, even in units where H bar is not 1.
Depending what I mean, it's a matter of convention. You can absorb it, but most books they just use h bar equal 1, so you don't see anything. You don't see where h is. Those who keep h, you can see both.
Okay.
I had the first version of my notes with 1, but because conventions in quantum theory, I decided to do it in this way. They are just conventions. I like it more at 1 here, but And I think at the end of the course they will make it 1 because it's more. That so far, looking different books, I think it's A dagger is creation because it creates a quanta, and A is annihilation. Creation and annihilation operator. Okay.
I know another question.
Please.
So, what I find interesting by reviewing quantum mechanics, you directly moved into a Heisenberg picture, no?
Yes.
So, which kind of connects to quantum field theory, where you define the Hilbert space after you have chosen your operator, algebra and so on. What I don't completely understand is at what point you have this shift of so here you have time-dependent operators, so it's X and P, and you just impose the canonical commutation relations to give you for every point in time operator satisfying some algebraic relation.
Right.
And so it seems that when you then build your raising and lowering operators and so on, you also construct later a Hilbert space associated to every time slice, and it's a priori not clear how these Hilbert spaces connect. Well, if you go back to the standard Schrödinger picture, the Hilbert space and all this structure you can define completely independently from the equations of motion, where here you take the equations of motion early on as an input to define actually X and P in terms of A and A dagger. So, yeah, I try to sharpen my understanding of this key point that is also relevant for field theory.
Right. So, I mean, your questions are very well posed because I am taking a shortcut. I am constructing this Fock quantization of the harmonic oscillator, which, as I would say in a minute, is different from the standard Schrödinger representation that we use. Later on in the course, in particular in chapter 10, I will dedicate certain amount of time to describe, to compare both quantizations and to tell you why they are different. Here, because I want to start pedagogically, I am presenting directly the Fock quantization because it's not completely analog to the case of the field theory. And it's true that in my shortcut, I am making jumps. In particular, I come directly to the Schrödinger picture. I could also do it in the Heisenberg line. I could also write this in the Schrödinger picture, and I will do it in that chapter. But for this first pedagogical chapter, I just wanted to do it in this way, which is parallel to the field theory. So regarding Heisenberg or Schrödinger, we can do both in both approaches. Regarding the Hilbert space, of course, in the Schrödinger picture is always L2 square, so the space of square integral functions. And what does depend on the equation of motion is the basis of eigenstates of the Hamiltonian that you use. It's a mid polynomial that depends on the dynamics. Here in the Fock quantization, what we have to do is to build what we call the one particle Hilbert space, and that is made of solutions to the equation of motion. So one needs to have the equation of motion to build this one particle Hilbert space, and from it to build this Fock space. So I agree, both quantizations are different looking, but they are completely equivalent to each other. So I will describe the relation more in detail later on in the course. But for these first lectures, I didn't want to enter in those fine details, so I don't lose students which are not so familiar with these topics. And I wanted, just for pedagogical reasons, to present the standard Fock quantization, which will be convenient later on. Is that fine?
Thank you.
Thank you for the question. So these are the way that these guys act, and additionally, something quite important is that the Hamiltonian operator can be written as, and this is something that we want you to check. It's a quick computation. Check that the Hamiltonian operator H hat can be written as H bar omega number operator plus 1/2 of the identity operator. This ID is just the identity operator. And as you know very well, this is quite important because this tells us that H and the number operator commute with each other. And you know from quantum mechanics that every time two operators commute, they share eigenstates. So, N, as a consequence of this, N and H operator share eigenstates. So all these eigenstates of the number operator, they are also eigenstates of the energy. And therefore, these states, labeled by some non-negative integer number, are eigenstates of the Hamiltonian, and the eigenvalue can be obtained easily from this solution, from this equation. This is H omega n plus 1/2. So this is the spectrum of the Hamiltonian, and from here we can identify what the vacuum is. So, one more thing I want to mention here is that you know that for the vacuum, the state with lowest energy corresponds to n equals 0. The energy is not 0, it's 1/2. So the lowest eigenvalue for the energy operator is not 0, it's 1/2. This is what we call the vacuum energy, or the 0-point energy. The vacuum energy. But in the absence of gravity, the absolute value of the energy is a convention. All what matters in physical applications are energy differences. So one can shift the energy to take out this 1/2 if you want to keep it. So sometimes people work with. So sometimes we work with what we call the renormalized Hamiltonian. So the renormalized Hamiltonian, let me call it just putting a couple of dots, dot and dot, is just the same operator without the 1/2. And I insist this can be done here because we don't have gravity, so the origin of energy is just a pure convention. So you will find this cat in some places. So, just to finish, the state with n equals 0 is what we call the vacuum, and is the ground state of the Hamiltonian. So this defines our vacuum. Then the state, or the state that we obtain by acting with A on the vacuum, is what we call a state with one particle state. They have not one particle, one quanta. They have one excitation over the vacuum. So they have energy H bar omega over the vacuum. So this state, there is only one. So it spans what we call the one particle Hilbert space. So doing linear combinations of that state, you get just a one-dimensional state that we call the one-particle Hilbert space. Here is one-dimensional. If we had two oscillators, it would be two-dimensional. So that n would be n-dimensional. And then you can keep building excited states, acting with a dagger on this one. You create a state with 2 quanta, with 3 quanta, with n quanta. And then the statement is that all linear combinations of states of the type n creation operators acting on the vacuum for all possible n's with integer n. So consider all possible multi-quanta states. Take all possible linear combinations. That is a space which we call the Hilbert space. So all linear combinations of those states form one technical point. They form what we call a dense subspace of the Hilbert space of the okay. Dense subspace the Fock. So this is just a name. The space of all linear combinations is called a Fock space. And this Fock space is our Hilbert space. Fock space is a particular case of Hilbert space. So the space in which we will do quantum mechanics is this Fock space. Again, made of linear combinations of multi-quanta. So regarding the previous question, this way of defining the Fock space is quite schematical. This is the way that people define the Fock space in books of quantum field theory. I find it quite a bit schematical because, at this point for me, all these states just look like symbols. I would like to know more about them, but for pedagogical reasons, I will do it later in the course. So far, we are going to start working with this Fock space, and later in the course, I will give you details of what is behind those symbols. How is the Fock space constructed? What is the inner product on it, etc., etc. But it's, for pedagogical reasons, it is better to do later on. So at this time, understand that this multi-quanta states is just the Fock space, vacuum, one quanta, 2 quanta, and all possible linear combinations among them. This is the space in which we work. We know how A dagger and A operate on that. A dagger operates in this way, A in this way. We know how the number operator operates. They are eigenvalues, eigenstates. We know how the Hamiltonian acts on it. We know how X acts on that because X is a combination of A dagger and A dagger. Also P. So we have all what we need to do computation. With these tools, you can do the computation that you want. And you also can check normalizations of these states using the computation operators, etc.
What are the other states in the Fock space? Is it a dense subspace or states at the bottom?
Right. So you have to construct Cauchy sequences of states and prove that they converge, and they converge to an element of the Fock space. But this is what I want to describe later on. So technically, I added this just to be technically correct, but I don't want to discuss that at this moment because that will deviate a lot. So just one more thing I wanted to say here is that using these computation relations, you can check, and this is also an exercise, you can check orthonormality or orthogonality between states. So you can check that if you take the inner product of one state with n quanta with one state with n prime quanta, only using the computation relations, you have to obtain h bar to the power n delta Kronecker n prime. And this is also an exercise for you. So the way of doing it is quite simple. A state with n particles is just n a dagger acting on the vacuum. So you make the ket, you put them together using computation relations, you move A to annihilate the vacuum, and you get a number at the end of the day. So just to finish, let me just summarize what we have done here. So, in summary, this very brief summary of the quantification of the harmonic oscillator. In summary, we have a Hilbert space. In reality, it's a Fock space. This multi-quanta state, and a representation of the position and momentum operators for every time. I just, unfortunately, erased was the x equal to a dagger, a function, a dagger, a function, a dagger function. This representation is called a representation because tell us how x and a dagger act on the Fock space. You know, we know how a and a dagger act, so we know how x and p acts. So it's a representation. This representation is such that first, x as a Heisenberg operator and p as a Heisenberg operator satisfy the equations of motion. So if you take those operators and you plug them in the equations of motion, they are satisfied. Almost trivially, because x and p were written as a combination of solutions. So any combination of solutions is always a solution. Remember that I was writing x a exponential with the root square plus a dagger exponential. So the basis, this was a basis of the space of solutions, so this will be also a solution because these guys are time independent. So if you plug this in the equation of motion, this will be satisfied trivially. So our representation satisfies the equation of motion. Second, our representation show that they are Hermitian. So we know that x and p have to be Hermitian. If you take the Hermitian conjugated dagger, this will become this will become this guy is Hermitian, is self-adjoint. So good. They satisfy commutation or canonical commutation relations. So if you plug this x and p and you use the commutations of a and a dagger, you obtain h bar I, trivially because these commutations were obtained from canonical commutation relations. So this also satisfies the canonical commutation. Quite trivially, but it's important to iterate that. And the last property, if you want, is that the vacuum state is invariant under the symmetries of our system. So what do you think is the most prominent symmetry in our system? So it's a time-independent oscillator, it's time translation invariant. The Hamiltonian doesn't depend on time, the Lagrangian doesn't depend on time, so you have the time translations as symmetry, the conserved quantity in the Hamiltonian, so the generator of that symmetry in the quantum theory is always unitary operator, which is the generator of time translator. And for convenience, I use here this normalized Hamilton. So if you add U in the vacuum, you get the vacuum. So the vacuum is invariant under the symmetries of our system. So if you want, we have a theory. This makes a theory for us. We can start computing observables and making physical predictions. We have all what we need. A Hilbert space and a representation that satisfies all these properties. We have that. So this completes the formulation of the Fock quantization of the harmonic oscillator in a way which is completely parallel to what we will do in field theory. I have a few comments, but they are wrong, so I will leave them for next day. One of the comments is that this is different but equivalent to the standard formulation in terms of predictive polynomials in the real line, but completely equivalent. But I will write that next day. So please keep this summary in your mind, because this is what we will follow. The same pattern will be followed in quantum field theory, both in Minkowski and Cartesian. So you have questions?
The very bottom right corner there, I wrote it out there. But is that the inner product of n and n prime equals h to the power of only n?
Yes, because there is a delta Kronecker and prime, so they have to be the same.
And n prime must be the same.
Right, because the Kronecker delta.
If they are equal, then they would.
Otherwise, you have zero.
Or then that's zero. Okay.
Any other questions? So I know this is familiar for all of you, but I think it's good to write them in this way. And in particular, next day, as my comments to close this chapter, I will make important emphasis in some structure which will be crucial for later on. So if there is any other question in the different places.
I have a question about how we said that this was a dense subset.
I didn't define that.
Yeah, but I could just be forgetful of my maths a little bit. But if we have countably many vectors as far as adding on the creation operator, right? So if we have a countable set of vectors, I don't see how that's dense, because I thought dense needed to be a little bit stricter than that. Or
You can do that. You will see.
Okay.
But those details, leave them for later on. If there are no questions, see you next Tuesday.
That's what the definition is. Yeah.
Well, thank you. We have nothing on?
Okay,
Bye.
go ahead.
Thank you. Bye-bye.
Bye-bye.
Thanks.
You are the only one who has.
Do you need this?
No, I have another copy, but I think I printed them on one page, only on one page.
Sorry for the stupid question about the H bar.
Please. No, it's not that stupid question. There are no stupid questions.
I actually got confused when I wasn't one.
This is what you have to ask. Sometimes for very important reasons, we get lost for some small details. So it's good to ask. Please keep asking.
Yeah.
Is the battery
So how do you want to calculate this?
almost finished? But it's just divided.
You have to have me assign a down in Skype, because otherwise I don't know for the sound.
But couldn't you?
No, I am doing it in my computer, because I also connected with the video, so the video record by the
but my Skype was open. I thought that you were going to add me as a contact.
I didn't want to.
Yeah, but it's
I want to make people connect, so I
Okay.
how easy is it for me to just look up from home?
I
How
would-
much?
no, no, it's fine.
Yeah, it's easy. Okay.
10 seconds.
Okay, okay.
I give you a password, an address and a password,
Okay.
immediately this.
Okay.
Uh,
I mean, I think I'll come for at least the first few times, but I just want, yeah, I want the option to sit around the table with my kids and stuff.
so there is, I can tell you, it's
How about you, Steven?
Yeah.
There is a